Okay, so this is the Edexcel Mechanics paper from June 2023. This is the last question on the paper, question 6. It's a classic ladder moments question with lots going on here. Not many numbers, unfortunately, so we have to kind of it's all a lot of algebra floating around. But anyway, let's look at it. So we've got this situation. I'll talk through it first, etc. What's going on. So we've got this rod AB, has mass M and length 2A, so remember that. The rod has its end A on a rough horizontal ground. As soon as you see that word rough, going to be some friction involved. So on the ground, we know it's rough, so there's going to be some friction involved down here. But its end B is against a smooth vertical wall, so there's going to be no friction involved with the wall. So establish that straight away, whether we've got friction or not acting on the ground and on the wall. So we have on the ground, haven't on the wall. Now it makes an angle of theta with the ground, as it's shown in the diagram. The rod is at rest in limiting equilibrium. Okay, so it's rest in limiting equilibrium. So if it's in limiting equilibrium, that means it's on the point of moving, but it's not quite. So that usually implies to us that friction, any friction involved, is going to be right at its maximum. It's going to be we're going to be using μr for its friction. Anyway, so let's get some stuff on here. I'll put the forces on there. Part A, you don't need to kind of have all the forces on there, but it says later on past part A, and so I'll put them on now. The magnitude of the normal reaction of the wall on the rod at B is S. So here, got a normal reaction coming out like this, and that's S. Okay, just a little note about this. Normal reactions, they're called normal reactions because they act at the normal to the surface. So perpendicular to the surface, basically. So if you've got a reaction coming out at from the surface and it's a normal reaction, it's always going to act at right angles. So you get questions like this where the rod is resting on a rail or something like that, and the normal reaction there acts out at right angles to the surface, like a bit of a circle theorem going on here. So normal reaction, it's normal because it acts at right angles. If it's just a reaction, and you get reactions just at hinges, then it could be coming off at any old angle. But normal reactions act at right angles to the surface. So we've got that situation there, with S coming off like that. It also tells us, having a quick look at it again, that the rod is uniform. So if it's uniform, its mass acts right in the middle. And we know its mass is M, so I'm going to stick in an M just there. Okay, then we have obviously a normal reaction here from the ladder pushing down onto the ground, so the ground pushes back at it, and let's call that R, shall we? And finally, our final force is going to be this friction. Now this is where part A comes in. It says state the direction, left or right, on figure 3 above, of the frictional force acting on the rod at A, and give you a reason for your answer. Now I think most people realise this rod is going to want to slip away down here. So friction is going to try and stop it, and it's going to act in this direction. So if I usually use FR for my friction, like that. So I think most people quite sensibly realise, friction is going to act that way because the rod wants to slip away from there. However, it's only a 1 marker, and part A, this was a lot of people not getting this mark, and this has appeared in a previous exam question as well. What the chief examiner really wants to see is you realising that actually friction there must be going in this direction because it has to oppose that S going that way. If this thing is in equilibrium, that means all forces in any particular direction must cancel out. So that means here, because we've got an S acting to the left, and it's the only force acting horizontally, friction therefore must be in the direction to oppose it. So that's the wording they're looking for. It's that kind of idea they're looking for. So I'll read out to you actually what they got on the mark scheme. So they said on the mark scheme, the normal reaction of B is acting to the left. So there, normal reaction is acting to the left. So friction must oppose it and therefore act to the right, as those are the only forces that are acting horizontally. No other forces being involved. So we just want friction must act to the right because the only other horizontal force on the rod is coming from the normal reaction at B, which acts to the left. So therefore friction must oppose it. Okay, so that's the kind of idea they're looking for. I know lots of people would just talk about, oh, the ladder's slipping away, so it must act in the opposite direction. Unfortunately, that didn't get the mark. They wanted you to talk about it being in equilibrium, and so therefore S being balanced off by friction. Okay, right, let's get on to the main crux of the question now. So we've got to use this model, and by taking moments about A, so they even give you a massive clue as what you're going to do, we need to show that S equals a half mg cot theta. Okay, so they even tell you where to take moments about, but hopefully that would be quite an obvious thing that you're going to take here, because if we're proving this, it's got m and theta in, obviously g in there as well, so there's no normal reaction or friction involved. This is the ideal place to take a moment about, because if you take moments about a point where any force goes through it, you can ignore that point, those forces, sorry, because the distance that those forces are away from that point is zero, so the moment caused is zero. So we're going to take moments about A. This should be actually quite a nice, straightforward one. Okay, oh, I better put some lengths on here, haven't I? Oh, I'll just put them in here. So that's A, and that's A because the whole length is 2A. Okay, now we've got to do a little bit of resolving here. So I like to, instead of kind of doing distance that m is away, we resolve these forces into two separate forces. So I'll tell you what, I'll do a little diagram here. So what I'm saying is that m that's coming down here, I'm going to resolve into two separate forces. I'm going to resolve it into a force that is perpendicular to the plane and a force that is parallel to the plane. So I'm going to resolve that m into two separate forces, and the reason we do that is because then this force can be ignored because its line of direction goes through A. So when you resolve it down there, it goes through A, so the distance its line of direction is away from the point is zero, it causes no moment. So it's just that force there that then causes the moment. And because it's a nice right angle, we can just go, oh, it's that length, that force times that length. So we're going to resolve that m down that away. Equally, for this force here, the S, we're going to resolve it into two forces as well, one going down that way and one nicely perpendicular there. So those are the two forces that we're going to do our moments about, resolving our forces. Now, looking at this, because that's theta, this angle in here is theta as well, because you've got 90 degrees triangle here, so that's theta, that's 90 minus theta, which makes that theta in there. So we're going through the angle to get to the resolving bit, so we use cos theta. So this has a, oh, I'll tell you what, silly me, it's got a massive M, so this should be mg there. Oops, apologies. So it's mg cos theta that is going through. Times its distance it's away is A. So mg cos theta A must be that force resolved that way, giving us our moment. And then over here, now, a little bit of alternate angles here. Theta there, little z going on there, so that's theta in there. So we are resolving that away from the angle, so it's sine. So we're going to do S, this is equal to, because that spins it that way, that spins it the other way, so it's equal to S, S sine theta times 2A. Now let's get rid of this little diagram here so it's easy to work through now. So there's our moments taken about A for part B. So we can tidy that up a little bit. Let's see, the A's cancel. That's nice. So we get mg cos theta equals 2s sine theta. Obviously have a look at what you're trying to make it look like here. So obviously cot's coming in, so dividing the sine over there will give us a cot. So we're going to get mg cos theta over sine theta equals 2s. Oops. Cos theta over sine theta, like we just said, is cot theta, so mg cot theta equals 2s. Now they're very picky in that you've got to make, if it's a show that, you've got to end with that line. So make sure whatever you're showing that, that's the exact line that you end up with. No kind of, that over 2 and everything. They started to be a bit nicer and let you get away with slight variations, but they're quite picky about these things. So just play it safe. Make sure that thing that you're trying to show is your very final line. So we're going to divide by 2. And you know what, they won't penalise this, but I'm going to do it. I'm going to write it out with the S on that side. Just so I get into that habit of making sure my last line is exactly what they say you need to show that. Okay, right. So, we've done part B. We've got ourselves 3 marks, hopefully, nicely. Now, we're then going to come on to part C. And it says, given that tan theta equals 3/4, find the value of mu. So, now the first thing, I'll keep that up there because that's part B done there. The first thing that we need to realise, and I'm sure you're all aware of this, but just in case, if tan theta equals 3/4, don't do your inverse tan and stuff like this. Tan theta equals 3/4 means that if that was theta on a right angle triangle, this would be 3 and this would be 4, 3 over 4 for our tan theta. And if that's the case, 3, 4, we can do Pythagoras to work out that's 5, or we know our Pythagorean triples. And therefore, we've now got sine theta and cos theta easily evaluated. Sine theta is 3 over 5. Cos theta, adjacent hypotenuse, 4 over 5. So we're going to be using those values, no doubt. Right, we need to find the value of mu. So, we know that forces up equal forces down, because this thing is in equilibrium. So the first thing to properly point out here, for part C, is that resolve forces vertically, and don't we nicely end up with the R equals mg? They must balance out. Okay? Equally, if we resolve forces horizontally, like was mentioned in part A, won't S equal FR? So S will have to equal the friction. We know what S is though, we know it's a half mg cot theta. So that's nice. Friction, it's at its maximum, is therefore mu r. Okay? But we know that r is mg from this. So now we're at half mg cot theta equals mu mg. Well, there's lots of things that cancel out there. The mg's cancel. So we're now at a half cot theta equals mu. Now, silly me, I went these for, we'll probably use these later, but if tan theta is 3/4, doesn't that mean that cot theta is 4 over 3? So therefore, a half times 4 over 3 is what mu is, and therefore mu is 2/3. Lovely. So don't ever forget that even with these ladder questions and everything, that it's not just about taking moments. If everything's in equilibrium, all the forces in any direction you want to take, if for any reason you want to take randomly, like perpendicular, they're going to cancel out as well. So any direction whatsoever you want to resolve forces, they're all going to cancel out if it's in limited equilibrium. Okay? So we've got ourselves mu equals 2/3. Right. Let's go on to part D. Just have to move the question down a minute, sorry. Okay, so find in terms of M and G the magnitude of the resulting force acting on the rod at A. Okay, the resulting force. So there are two forces acting on the rod at A. There's our normal reaction and there's our friction. So therefore, we need to resolve those two forces into one overall force. That's what it's asking for. So when it says, find in terms of M and G the magnitude of the resultant force, so whenever it says resultant force, that means we're having a few forces together acting on the rod at A. So the two forces acting on the rod at A, friction and the normal reaction. So we're going to put those two together to get the overall force. Now, we know what R is, it's mg. We also know what friction is, it's mu R, which is mu mg. We know mu is 2/3. So I'll just write those down here before I rub it off. We know R is mg, and we know friction is mu mg, which is now 2/3 mg. Okay, so part D. Two forces, friction going this way, 2/3 mg. Reaction going up that way, mg. So the resultant force is that force there, little force triangle if you like. So we're just going to do, and it wants the magnitude, so that means just how big it is. We're not interested in what angle it's going off at or anything like that, although that's quite easy to work out because it's, yeah, anyway. So we're just going to do a little bit of Pythagoras involving these. So the resultant force, what are we going to call that? I don't know, just let's call it F or something like that. So F equals mg squared plus 2/3 mg squared square rooted. That is going to be our resultant force. Now, you can mess around with this, but hopefully you realise that these mg squareds are then, when they square rooted, are just going to become mg, but I'll go the long way if you want. So it's m squared g squared plus 4/9 m squared g squared square rooted. 4/g, that's maybe 4/9, sorry. 1 m squared g squared plus 4/9 m squared g squared is 13/9 m squared g squared. And when you square root that, well, square root of 13, no thank you. Square root of 9, 3. Square root of m squared g squared, surprise, surprise, is mg. So you're going to get root 13/3 mg. Okay? So, just moving me thing down, excuse me for a second. Okay. Now then, final part, it's another one marker. So it's another one where you have to kind of think a little bit about what's going on here. So let me just write this off. Let me just get a better pen because this is starting to run out a little bit. Okay, so the question says, in a new model, the rod is modelled as being non-uniform, with its centre of mass closer to B than it is to A. Okay? A new value for S is calculated using this new model with tan theta equals 3/4, so the tan is going to be exactly the same. State whether this new value for S is larger, smaller, or equal to the value that S would take using the initial model. Give a reason for your answer. Okay, so we're after whether S is going to be larger or smaller, etc. Now, if mg is no longer there, remember what we did for the very first part, where we were taking moments about A. If we took moments about A, it just becomes a straight off moments battle, if you like, between the mg and the s. So if this was not in the centre there, if it was closer to B, that means the distance it is away from A is larger. So when we take our moments and we go, oh, let's resolve that and do that times the distance, because the distance is larger, the moment caused by mg is going to be bigger. And therefore, if the moment caused by mg is going to be bigger because it's further away, so we'll be times in by a bigger distance, the moment caused by mg is going to be bigger, the moment caused by s is going to have to increase to be able to match it, to cancel it out. So because mg is going to start causing a bigger moment, that means s has got to up its game. S has got to be bigger now to be able to match it in terms of moments and cancel out. Now s hasn't moved, s is still there, so the distance can't change, so s itself must increase. So s is going to be larger, and the reason we're looking for is because the moment caused by mg is going to increase because it's further away. So moment caused by the mass is larger as it's further away from A. What's that going to say, A? Okay. Therefore, S must increase to, how should we say this? S must increase to provide, this is terribly clunky, but I hope you understand what I'm talking about there. A bigger moment to cancel out the moment caused by M. This pen's terrible for writing, but never mind. Anyway, so I hope that makes sense. That's moving away, so it's causing a bigger moment because we've got a bigger distance we're going to have to times by. So that's going to have to increase because it can't change its distance, it's away. So it's going to have to increase the actual value of S so that it can match the moment being caused by that mg. Okay, quite an interesting question that. 13 marks, a lot going on there, and hopefully a lot of things you can take away from that.